All right, let's just dive right in. In this explainer, we're tackling something absolutely massive. We're looking at how the most mind-bending ideas in all of physics, think the speed of light, space-time, went from, well, crazy intuition to hard, proven reality. We're going to see just how profoundly strange our universe really is, and how science actually manages to drag these weird truths out of the mathematical shadows.
To kick things off, we really have to ask a deceptively simple question. What exactly is time? It's a total paradox, right? Because we viscerally experience it every single day. We instinctively know today from yesterday, but formally, conceptually, it completely evades us. And this basic, everyday mystery, that's exactly where our journey begins today.
So let's get into it. Section 1, the illusion of universal time. This is literally the ultimate clash of scientific titans. On one hand, you've got Isaac Newton's highly intuitive belief, time is just a universal ticking clock. Basically, whether you're right here on Earth or hanging out way over on Alpha Centauri, you experience the exact same flow of time. Makes sense, right? But then, bam, we had Albert Einstein's 1905 breakthrough. He mathematically proved that time is utterly relative. He showed that different people, moving at different speeds, actually experience time differently. I mean, it's a concept that completely rewrote the rules of the universe.
Which brings us to Section 2, unifying space and time.
The way hundreds of years of standard physics escalated here is just rapid fire. We started centuries ago with Galilean relativity. The idea that the laws of nature are the exact same whether you're sitting perfectly still or moving at a constant speed. From there, we jumped to Einstein's famous 1905 miracle year. But here's the wild part. It was actually one of his teachers, Hermann Minkowski, who looked at Einstein's equations in 1908 and realized the ultimate truth. He formally proved that space and time are, well, they're pretty much the exact same interconnected thing.
So the crucial point we have to grasp here is that space-time is a unified physical map. And later, general relativity came along and showed us that gravity isn't some invisible string pulling things together. Not at all. It's the actual crinkling, bending, and warping of this space-time map. Think about it. If you're in an accelerating, totally quiet rocket ship, it feels exactly like gravity. Einstein took that realization and concluded that gravity itself is just the geometry of space-time bending around massive objects. It's a staggering leap of imagination. It literally changes how you view something as simple as dropping your keys on the floor. Now, to really empathize with how incredibly hard of a conceptual leap this was for folks back then, let's think about chemistry for a second. You have sodium, right? A highly explosive metal, and chlorine, a deadly, toxic gas. Two absolutely terrifying elements. But if you bring them together, if you unify them, you get table salt, something totally innocuous and absolutely necessary for human life. Unifying space and time was a whole lot like that. They took two fundamental, completely distinct parts of our reality and just merged them into an entirely new truth.
Moving right along, let's look at Section 3, the ultimate speed limit.
Because here is the very premise that made all of Einstein's weird physics possible in the first place. The speed of light is the same for everybody, irrespective of how we are moving with respect to each other. Now, this single rule totally pegs the weird meter. It completely defies everyday logic. Like, if I drive a car toward you while you shine a flashlight at me, common sense absolutely screams that the light is moving faster relative to me. But it's not. Everyone measures the exact same number. But once you embrace that this speed limit is simply a fundamental property of space-time itself, all the weirdness of relativity, it just falls perfectly into place.
And the coolest part is that modern particle physicists actually test this assumption today. They use hard, serious measurements that were absolutely impossible during Einstein's era. Here's how they do it. Step 1. Collide two subatomic particles together. Step 2. The newly created particle decays and emits photons, or light. And Step 3. Measure the time it takes that light to reach a surrounding detector. It sounds simple enough, right? But the results are what will completely blow your mind.
Because here is the definitive proof. If the created particle is perfectly stationary, the light hits the detector at exactly the speed of light. Fair enough. But what if that created particle is flying out of the collision at 95% the speed of light? Common sense dictates the light it emits should travel way faster, right? Cutting the travel time down? Nope, no way. It takes the exact same amount of time to hit the detector. The assumption leads to predictions. Those predictions are measured to be true, and therefore the assumption is definitively, undeniably true.
Which leads us to our final part, Section 4, the anatomy of genius.
So if these concepts are so utterly counterintuitive, how in the world do scientists actually generate these ideas? And more importantly, how do they force the culture to accept them? Well, history shows this gradual, staggering march toward accepting smaller and weirder building blocks. We tell little kids today that the world is made of unseen atoms, and we do it without a second thought. But remember, we went from vaguely theorizing atoms to finding the nucleus, then electrons, photons, all the way down to quarks. Basically, as we dive deeper, reality gets weirder, and the culture just has to slowly adapt to this new foundational reality.
Take the theoretical physicist Paul Dirac, for instance. He took what honestly sounded like an absolute leap of faith, based purely on math, to correctly predict the existence of antimatter. The equations indicated it should be there, and instead of brushing it off as some weird mathematical glitch, he actually took it seriously. It sounded completely insane at the time, but guess what? The math was right on the money.
Because being a genius in this field requires way more than just a creative idea. It's a very specific amalgam of traits. You need that historical context and deep mathematical discipline. You absolutely need that rare intuitive spark, that aha moment. But here's the kicker. That spark must be paired with downright jerky, combative critique. Let's be real. Most ideas in science are wrong. So you need ruthless peer review to kill off the bad ideas so you don't waste time on them. And that is exactly how you prove the good ones.
And there's a beautiful historical irony here with Einstein himself. While he generated this grand aha moment for relativity, he actually couldn't accept the absolute insanity of quantum mechanics. It was just way too weird for him. But his deep, rigorous, combative critiques of the field, they were absolutely essential. He forced other scientists to go out and rigorously test his pushback, which, ironically enough, led them to successfully prove that mind-bending things, like quantum entanglement, were actually tangibly real. His own critiques advanced the very science he doubted.
It all really comes down to the true ethos of theoretical physics, which was perfectly summed up by Niels Bohr when he told a colleague, "We all agree that your idea is crazy, but is it crazy enough?" To fundamentally change how we see the world, you have to take massive, crazy leaps of faith right into the unknown. But those leaps absolutely must be backed up by intense mathematical rigor and relentless testing.
So to wrap up this explainer, I really want to leave you with a final provocative thought. What unifications are we entirely blind to right now? Think about it. If space and time were hiding in plain sight all along, just waiting for someone to finally do the math, what other massive, universe-altering unifications are sitting right in front of us today? It really makes you wonder what the next century of physics is going to reveal. Keep asking those crazy questions, guys, and I'll catch you in the next explainer.